Our dynamic universe. The key areas covered will be force-time graphs during contact of colliding objects, impulse found from the area under a force-time graph, equivalence of change in momentum and impulse, and Newton's third law of motion. What we will do today is state what is meant by impulse, investigate force-time graphs, and use these to calculate impulse. Impulse. An object is accelerated by a force F for a time t. The unbalanced force is given by F equals ma. We can replace this acceleration with an equation that we already know, v take away u over t, and this v take u can be expanded out with our m to be mv take mu, still divided by t, and so our unbalanced force is a change in momentum divided by time, because we know momentum is mass times velocity. This unbalanced force is equal to the rate of change of momentum. Impulse is change in momentum, which is unbalanced force times time. We can write this as mv take mu divided by t multiplied by t, and so impulse itself is mv take away mu. The units of impulse are kilogram meters per second or Newton seconds. Impulse is a vector quantity, so direction is important. The concept of impulse is useful in situations where the force is not constant and acts for a very short period of time. An example of this is when a golf ball is hit by a club. During contact, the unbalanced force between the club and the ball varies with time, which is often given in milliseconds, as shown in the graph opposite. We can see a sharp increase in force and then a sharp decrease in force over a short period of time. Making use of impulse. We can make use of impulse to help with safety features. Rearranging the equation to force equals mv take mu divided by t shows that to decrease the force, you have to increase the time of contact. This is why cars have a crumple zone and why helmets have padding inside. These safety features increase the time of contact, which decreases the average force applied, decreasing the damage on the human body. This can be expressed in graph form. Note the change in momentum does not change. Mass, initial velocity, and final velocity are all the same. We can see that without a crumple zone, we have a high force in a low time, and when the crumple zone is introduced, our time increases and therefore the average force decreases. Newton's third law. For every action, there is an equal and opposite reaction. This holds true for impulse. The force created during contact between the two objects, i.e. a golf club and a ball, is equal. Bouncing balls. This effect can also be seen when using balls of different materials. A hard ball, such as a basketball, deforms only a little. A softer ball, such as a squash ball, deforms more, and so the time of contact is longer. In practical situations, the force is not constant, but comes to a peak and then decreases. Impulse is equal to area under a force-time graph. In any collision involving impulse, the unbalanced force is calculated is always the average force, and the maximum force experienced would be greater than the calculated average value. Time is often given in milliseconds, but this must be converted into seconds. A snooker ball of mass 0.2 kilograms is accelerated from rest to a velocity of 2 meters per second by a force from the cue which lasts for 50 milliseconds. What size of force is exerted by the cue? First, we want to write down what we know and what we don't know. So we know our mass, that's 0.2 kilograms. We know our start speed, that's 0 because it's from rest. We know our end speed, that's 2 meters per second. We know our time, that's 50 milliseconds. We need to write this in seconds, remember, so that's 0.05 seconds. And it's the force that we want to work out. So our equation is going to be Ft equals mv take mu, and let's just substitute in our numbers here. So F times 0.05 equals 0.2 times 2 minus, and then this is going to be equal to 0 because our u is 0. So rearranging this to give F, we get F equals 8 newtons. A tennis ball of mass 100 grams, initially at rest, is hit by a racket. The racket is in contact with the ball for 20 milliseconds and the force of contact varies as shown in the graph. What was the speed of the ball as it left the racket? Again, let's write down what we know and what we don't know initially. Our mass is 100 grams, which is 0.1 kilograms. Our initial velocity was 0 meters per second because it started at rest, and our end velocity is what we want to work out. Our time, we can see, is 20 milliseconds, which is 0.02 seconds, but we don't know our force. We can see our maximum force there is 400 newtons, but we need to know our average force. So we know that impulse is equal to area under the graph. And we write this as a half times base times height, because it's a triangle there. So we've got a half times our 0.02 seconds. Oh, we don't need to include our seconds in there. Times by 400. This equals 4 Newton seconds. This Newton seconds is equivalent to our Ft in our equation that we're going to use. So Ft equals mv take mu. 4 equals 0.1 times v minus, again we know this is 0 because our initial speed was 0. So rearranging that, we get v equals 40 meters per second. A golfer hits a ball of mass 5 times 10 to the negative 2 kilograms with a golf club. The ball leaves the tee with a velocity of 80 meters per second. The club is in contact with the ball for a time of 0.1 seconds. What is the average force exerted by the club on the ball? Let's write down what we know and what we don't know. So our mass is 5 times 10 to the negative 2 kilograms, which we can write as 0.05 kilograms for ease. Our initial velocity, it says the ball leaves the tee with a velocity of 80 meters per second. So initially the ball was just sitting on the tee, so it's at rest at 0 meters per second, and our end velocity is 80 meters per second. Our time is 0.1 seconds. Notice it wasn't given in milliseconds this time. And our force is what we need to calculate. Let's write down our equation. Ft equals mv take mu. And substituting in our numbers, we have F times 0.1 equals 0.05 times 80. We know this mu is going to equal 0 because our u itself is 0. So this is take 0. Rearranging this, we get F equals 40 newtons. This corresponds to an answer of E. The graph shows the force acting on an object of mass 5 kilograms. What is the change in the object's momentum? We know that change in momentum is equal to impulse, which equals the area under a graph. So we need to work out the area underneath this graph. Let's add in a line to make it easier to figure out our area. We can label this part A, this part B, and this part C. So our areas. Part A is going to equal a half times base times height because we've got a triangle. So a half times the base is between 0 and 1, so we've got 1. The height is between 10 and 20, so we've got a height of 10. Therefore we have 5. And again, this is in momentum, so it's kilogram meters per second. The area of B is just going to be base times height because we've got a rectangle there. So that's 1 times 10. So that's going to be 10 kilogram meters per second. And C is going to be a half base times height, which is a half. Our base this time is between 1 and 3, so that's 2. And our height is between 0 and 20, so that is 20 there. So our area of C is 20 kilogram meters per second. Our total area is just adding those up. So we've got 5 plus 10 plus 20 is equal to 35 kilogram meters per second. This is an answer of C. The graph shows the force which acts on an object over a time interval of 8 seconds. What is the momentum gained by the object during this 8 seconds? Again, we know the change in momentum is equal to the area under the graph, so let's work out this area. We can say that this rectangle down here can be labelled A, and this triangle up here can be labelled B. So our areas, A is going to be just base times height because it's a rectangle. Our base is between 0 and 8, so that's 8. And our height is between 0 and 4, so that's 4. 8 times 4 is going to equal 32 there. Let's look at area B. We've got half base times height this time. This equals a half. Our base is between 4 and 8, so we've got 4. And our height is between 4 and 10, so we've got 6. A half times 4 times 6 is going to equal 12. Our total area is going to equal 32 plus 12, which equals 44 kilogram meters per second. This is answer C. A car is designed with a crumple zone so that the front of the car collapses during impact. We want to know the purpose of the crumple zone. So already we can see that C says to decrease the driver's final velocity. The final velocity is going to be 0 no matter what happens because the car is going to come to a stop. So we can initially say that's wrong. D and E are talking about increasing and decreasing the total change in momentum. Because our mass, our initial velocity and our end velocity are all not changing, this total change in momentum is going to stay the same. We can't increase or decrease that. So again, we can ignore those. Between A and B, we either want to decrease or increase the change in momentum per second. Ideally, we want to decrease the change in momentum per second because that decreases the force on the driver. So increasing this would increase the force. We definitely don't want that to happen. So our final answer is going to be A. Decrease the driver's change in momentum per second. Car X is designed with a crumple zone so that the front of the car collapses during impact as shown. A similar car, Y, of equal mass is built without a crumple zone. In a safety test, both cars are driven at the same speed into identical walls. Which of the following statements are true during the collisions? Let's take them one by one. The first statement says the average force on car X is smaller than that on car Y. We can say yes, the average force is smaller because it's spread out over a longer time. This crumple zone is there for a reason. It's reducing this average force, it's keeping the driver safe. The second statement is the time taken for car X to come to rest is greater than for car Y. Again, we know this is the purpose of the crumple zone. It's to increase the time taken for the car to come to rest. So the second statement is correct. The third statement says the change in momentum of car X is smaller than that of car Y. If it said change in momentum per time, we could say that's correct. However, the total change in momentum, again like for the last question, is going to be the same for both. Because our mass is not changing, our initial velocity is not changing, and our end velocity is not changing. Therefore, the momentum cannot change. So this is wrong. If it's just 1 and 2 that are correct, then our answer is going to be B. Here's an open-ended question from a specimen paper. A picture of a helmet designed to be worn when riding a bicycle is shown. The bicycle helmet has a hard outer shell and a soft expanded polystyrene foam liner. Using your knowledge of physics, comment on the suitability of this design for a bicycle helmet. Here is a possible solution. The hard outer shell absorbs some impact from the road. The soft polystyrene foam liner increases the contact time of the head. Using the equation F equals mv take mu over t, it is clear that to decrease the average force on the head, contact time should be increased. Decreasing the average force results in less damage to the head. Here's another open-ended question from 2012. Tennis players are coached to swing through the ball when striking it rather than stopping the tennis racket suddenly. Using your knowledge of physics to comment on why this causes the ball to leave the racket with a greater speed. Here's a possible solution. Compare hitting the ball with and without swinging through the ball and use the equation Ft equals mv take mu. In both cases, the mass of the ball and the initial velocity are the same. If we take u to equal 0, then Ft equals mv. Assume that the racket used is the same in both cases and applies the same force F. Not going through the ball means a shorter contact time. And if the contact time is small, then so is Ft and mv. As m is a constant, then final velocity v is small. Going through increases the contact time, increasing Ft and as a result increasing this velocity.